and thank you for attending today's webinar. This is Amy St. Croix with the Statistics Division. Our speaker today is Dr. Jack B. ReVelle, a consulting statistician at ReVelle Solutions. And not only does Jack provide his technical assistance as a quality and industrial engineering expert to attorneys involved in litigation, but he also gives advice and assistance to manufacturing, service, residential, construction, and service organizations around the world. Jack is also a former leader of continuous improvement for Raytheon Missile Systems Company and former director of the Center for Process Improvement at GenCorp Aerojets. Before earning his PhD in industrial engineering and management from Oklahoma State University, Jack also served 12 years in the United States Air Force, where he was promoted to the rank of major and awarded several honorable medals for his work in quality assurance. Today, Jack will be presenting on Making the Connection, which was a popular talk that provides an overview of tools used to collect and analyze quantitative data, as well as a variety of other purposes. During the webinar, all phones and microphones have been muted, except for that of the presenters. So if anyone has any comments or questions during the webinar, please feel free to use the questions interface in the GoToMeeting panel. I will relay those questions to Jack at the end of the presentation so that he can answer those for us. So without further ado, I'm going to hand things over to you, Jack. And again, we thank you for presenting with us today.
Thank you, Amy, and hello, everybody. I'm here in Orange County, California, the land of sunshine and earthquakes. And I'm going to be talking today about making the connection, as Amy just pointed out. As you can see on your screen, this idea, this concept of quality tool connectivity was conceived of and developed by the U.S. Air Force quite a while ago, September 1989. And that's when I first became aware of it. Then in talking with Ellen Dome, who at that time was the founder and editor of the Trees Journal, I was invited to publish an article about connectivity, and did that in July 2008. And then about 2 years later, an expanded version of the same material was published in Quality Progress. And the same month, the China Association for Quality had seen my article in Quality Progress and requested permission to translate and republish the material, which they have. And I got a copy of it. I think it's my material, but I can't be positive because my Chinese is limited to 0. The origin, as I mentioned earlier, the connectivity concept was developed initially in late 1989 by a captain in the U.S. Air Force, and he called it the variability reduction process, and it continues to be referred to that in some circles, and I've provided that as a separate ASQ webcast, which can be acquired through the folks in Milwaukee. Oh my. Here's the agenda, a couple of pages of agenda. We'll talk about the 7 QC tools, and then we'll talk about connectivity with the QC tools, and then connectivity with discussion focused on trees, the voice of the customer, the Kano model, quality function deployment, the 7 management and planning tools, and design of experiments. Then we'll get into a detailed discussion of the voice of the customer, detailed discussion of the Kano model and voice of the customer tables, of which there are 2, and then turn our attention to the paired comparisons process, then prioritization matrix, the benefits of quality function deployment, specifically the initial matrix, the house of quality. And then we'll talk about process flow in quality function deployment. And then I'll introduce you to a new concept selection process flowchart which I developed several years ago for use with a client. And then we'll turn our attention to the robust design of experiments and take a look at an L8 orthogonal array. And as we turn to the end, we talk about connecting two problem-solving tools, specifically cause and effect analysis and design of experiments. And finally, we'll talk about the connectivity chain. But that's what this telecast, broadcast, webinar, webcast, whatever you want to call it, is all about. First, not knowing the backgrounds of everybody, of some 130 people signed up to participate in this particular webinar, so I don't know everybody's background. I'm sure some people are highly experienced statisticians, far more than myself. Others may be brand new to the field. For those of you who may not be familiar with it, there's a thing called the 7QC, or quality control tools. They include data tables, which are both check sheets and tally sheets, cause and effect analysis, histograms, Pareto analysis, scatter analysis, trend analysis, which includes graphs and run charts, and finally, statistical control charts, both for attribute data and variable data. And we'll be talking about all of those and how they fit into the concept of tool connectivity. Now, I put this chart together when I first put the concept of making the connection together for the Trees Journal, which is an online journal. And I put that all together, and I'm going to use this as kind of the skeleton or the process flow chart for what we're going to be talking about this morning, or in the case of everybody else, I guess, in the afternoon. First, we'll talk about process flow charts and process maps and how they relate to each other, and then you'll see we'll move on into a split pattern with the material on top being for attribute or discrete data, and the material just below it moving on from left to right, talking about continuous or variable data. But first, let's compare process flow charts and process maps. At the top of this graphic, you can see a process flow chart. It's got 7 steps, and it goes in series in steps 1, 2, and 3. We get to a decision point in step 4, and there's an opportunity for a go, no go, meaning maybe a defect or no defect, insufficient time, sufficient time, whatever it might be. And if it's unacceptable, it goes back to step 2, or it could be to step 1 or step 3, but simply for this point of discussion, just to show that there are 2 paths coming out of step 4. And from there we go to a parallel mode, steps 5 and 6. Both are started at the same time. They finish at different times, but both have to be complete before you can go into step 7. Now, that's a simple, straightforward process flow chart. Let's look at the same 7-step process using a process map, which is at the bottom half of the same chart. You'll notice over on the far left the letters A, B, and C in process map. And down at the very bottom of this graphic, it says A through C are process stakeholders, persons, departments, it may be buildings, it could be anything that you designate. And let's say that there are 3 process stakeholders involved in this particular process. And step 1, which you saw in the process flow chart above, is being handled or is the responsibility of stakeholder A. And then step 2 the process goes down to stakeholder C, and step 3 it goes up to stakeholder B, and step 4 goes back up to A. And then of course, just as we had in the process flow chart, the no-go decision takes us back to step 2 as it did in the process flow chart. And if it's acceptable and we go into a go mode, we go to steps 5 and 6 with stakeholder B being responsible for 5 and stakeholder C being responsible for 6. And what I said earlier, well, 5 and 6 being started at the same time, but both having to be complete before we can move on to step 7, which goes back to stakeholder A. And you say, okay, that's certainly more detailed, a clearer vision of this process. But why do we do that? Well, one, it's terrific for training, so people or organizations know where their work is coming from, who it's going to, who they're responsible for. It's also very good for identifying where processes can be simplified. Do we really need another stakeholder, or can this be condensed? All kinds of more detailed, responsible analysis is possible using a process map as opposed to a process flowchart. A few years ago, I was working for a major home builder, and we had a room the size of a basketball court that was covered with butcher paper all around the walls, and we were putting up Post-it notes, putting up process maps, starting with the concept of designing the home and finishing with the construction of the model homes and the movement of possible customers into the model homes to view these homes and see what was going on. All kinds of insights were gained about the process that they had been using in the past, and as a result, major changes were made. They were extremely pleased. At any rate, that's the difference, the advantages of process flowcharts versus process maps. Moving on, now let's talk about attribute and discrete data versus continuous or variable data. And as you can see just to the right of those two blocks, we have control charts for each one. For attribute control charts, we have C charts, P charts, and NP charts. And for variable control charts, we have X bar and R charts, and there's several others as well. But let's move on, and you'll see what happens. First, we have to decide, before you decide whether you're going to use attribute or continuous data, you have to decide what data needs to be collected. What's your performance metrics? What's really important about this particular process? Well, there's several different kinds of data, and there's 4 charts here that I've got, and you can see this is types of data 1. We're talking about the data types being nominal, ordinal, interval, and ratio, and I'm going to limit discussion on that right now because I've got to, after we go through types of data 2 and 3, we'll go to types of data 4. And Amy, you don't have that one yet because I created that chart last night. So bear with me here, folks. We also have attribute or discrete data. Under that, we have nominal or ordinal, and we have when they're being used. And in types of data 3, we have continuous or variable data. Again, interval versus ratio, and how they are used. Now, let's go to data 4. This, Amy, you've not seen this before. I put this together, as I said, last night. Starting on the far left, we have 2 types of data, attribute or discrete equivalent names, or continuous versus variable. And then you have data classes, the 4 data classes that we saw in an earlier slide. Within attribute and discrete, there's nominal and ordinal. And within continuous or variable, there's interval versus and ratio. Now, what's the purpose of each of these? Well, for nominal, it's for counting defects, and it's the highest frequency of use of all the different types of data. And for ordinal, you have rank ordering, and that's the least used. And for interval, we have rating scales, which are moderate use, and ratio, which is physical measurements. And there's like nominal, that's of the highest use. And over on the far right, I've given some examples of applications for each of these. For example, for the attribute and discrete data called nominal, we use that for counting occurrences or for numbers on players' uniforms. Again, for attribute or discrete data, we have ordinal, and that's used for identifying first place or second place or more in a rank ordering. And for continuous or variable data, we have interval, and that's used for IQ tests or for identifying grade levels in schools. And finally, still with continuous or variable, we have the class ratio, which is physical measurements. And again, that's of highest use, and that's for use with truly continuous data, such as length, time, mass, and the like. I think this is a really good slide for trying to bring all the different types of data classifications together so that people can understand them better. I think it would be excellent for use in a basic course on math. Anyhow, moving on, we have to decide how we're going to collect the data. We're either going to count it or measure it. Now, for attribute or discrete data, this lady on the left has decided to count. And for measuring, the gentleman with the tape measure and the pencil over his ear and his tongue hanging out is going to use that particular methodology for continuous or variable data. Now that we've got that idea taken care of, let's move on. And here's an example of an X bar and R control chart. There's not a lot of people around that know that I owned until just a few years ago a ranch in Arizona and a big sign out front at the main gate and said, "This is the X bar and R ranch." You know, everybody around had ranches like, you know, the rolling X and the lazy L and all that. And I just thought it'd be great to have an X bar and R ranch, and so I did. And the X bar chart, of course, is used to measure, in this case, shaft diameters, and the same, of course, with the R chart. The X bar chart is looking at precise measurements, whereas the R chart is looking at ranges between measurements in a particular subgroup. Now we use zone rules to identify when a process is in or out of control. And those zone rules apply equally across the board to all of the various charts that we talked about. But if you'll put a hand up to your screen and cover the material just to the left, just to the right of the vertical dashed line, and so all you're going to see is the material on the left side of the chart. That's known as the pre-intervention, before we do anything. And we can see where the upper and lower control limits are in red, and the center line of the process. And you can see that, you know, this is the status of the process without regard to saying whether it's good, bad, or indifferent. Now take your hand away, and the intervention, the corrective action that's been introduced has been completed, and now we're looking at the resulting data on the same process. And as you can see, there has been a major shift in the process going from left to right, and the center line of the process has been reduced significantly. The upper and lower control limits are such that the upper control limit of the post-intervention status is only fractionally above the lower limit of the pre-intervention status. And this, by the way, is what we saw the very first time I used an X bar and R chart on a real-world process. Was on a wave solder process working for Hughes Ground Systems Group in Fullerton, California. That doesn't exist anymore, but we had a wave solder process, and we had circuit cards that were going through a wave solder process, and they had a high level of defects. And as you can see, looking on the left, the process was going crazy in terms of way too many defects. Things like solder missing, excess solder, etc. And after we did our intervention, the intervention, by the way, was correcting the support frames that the circuit cards were being held in as it went through the liquid solder. And when those things were warping because they'd been around for so long and nobody had checked that. And once we replaced all those frames, the boards were going through smoothly through the liquid solder, and you can see that the defect rate went way, way, way down. So this is a good way to share information like this with the people who you may be responsible to, or trying to explain why something has happened or why it hasn't happened. Now let's talk about trend analysis. Trend analysis doesn't depend on the type of data being examined. That includes both attribute or discrete data and variable or continuous data. And they can even be plotted on the same trend chart. For example, so we could have a scale on the left side of our graphic for attribute or discrete data, and on the right side for variable or continuous data. And in blue, we can see the actual plotting of the points in the solid blue line and the solid red line, and the trend line or the slope being plotted with the dashed line. And you would normally see a chart that, if you were using a chart like this, as we move from left to right, you can see that you get very different data. But variable or continuous data costs more, takes longer to collect, and is more, I hate to use the word difficult, but it's more complex to analyze than attribute or discrete data, which is very easy to collect and costs very little. But you get so much more information out of variable or continuous data that we always encourage, wherever possible, that with the performance metrics that we use to evaluate a process, that that wherever possible you want to use variable or continuous data. But for the sake of presentation, I just wanted to show that on the same chart you can plot for the same process over the same period of time both types of data and see what the difference is and what it looks like. Moving on, you can also do it when you've got data going in opposite directions, as we have on this particular chart. Okay, now we're moving over and we're ready to move from data collection onto tally sheets. And there on the left is a simple tally sheet. And I'd be willing to bet that every one of you has seen a tally sheet or even used one in your own personal life. But there it is on the left, let's say with the frequency of how frequent something occurred for, let's say, 6 items. And you can see the tally marks in the center column. And then when we're all finished and we've looked at everything, we sum them up, and there's the grand total at the bottom. And a run chart, which is kind of an interesting approach to a run chart, is strictly for looks at this point. Now we're ready to talk about data analysis. And you see where the two lines for attribute data and continuous data continue on. We're using A for the attribute data and B for the continuous data. And then we drop down to the bottom half of this chart, and A re-enters the process with Pareto analysis for the attribute or discrete data and histograms for the continuous or variable data. So let's take a look at those. The data analysis tools that we're going to use are many, and I've listed just some that I would imagine every one of you has seen one time or another. There's far too many for me to discuss in the brief time that we have available. And so let's take a look at the randomization. How do you select samples? Well, let's suppose that we've got a lot of people do it now, using the computer, but for purposes of teaching, and I would guess many of you might be teachers, over on the far left, we begin with 2-digit random numbers. It could be a 1-digit random number or a 3-digit or 6-digit. But on the far left, under the word random, we've got a series of random numbers that were selected, for example, out of a random number table or generated in some other way. Just to the right of that, just to the right of the arrows, we take those numbers and we're going to divide them up into 2-digit random numbers. And so we have in the first row 34, 17, and 29. We could just as easily have done it for 3-digit random numbers, and that would be 341 and 729. Or a 6-digit, and we just use the entire number. But for the purposes of this demonstration, we'll talk about 2-digit random numbers. And you'll notice at the very bottom, under the 2-digit random numbers, there's a block there that says there are no 00 unit tag numbers, so no unit is selected. Now the tag numbers are in the center of this chart. What we've done prior to the selection, either prior to or after the selection of the random numbers, is we've given each item in the population that we're examining a tag number. And let's suppose that there are 50 items in the population that we're looking at. It might be a lot of product or something of that nature. And let's say that there's 50 of those. And so now what we want to do is apply the 2-digit random numbers to the population unit. And we find that the very first one in red you see in the column on the right, the third row down in the two-digit random number is 04. And so we locate 04 in the population units, and that tag number tells us that that unit that has the tag number 4 is going to be one of the items in our sample. And we find 07 in the third row of the two-digit random numbers, and in the center of the third row. And so we identify 7 as being the a part of the sample out of our 50 population units. And we'll continue that. We find there's 25, and a variety of others. And each of those has been identified. And so we end up with all of those over on the far right. The result is that we have the selected units in the sample are 04, 07, 17, as well as all the rest. I didn't put arrows from the two-digit random numbers on the far left of the screen to the population unit tag numbers in the center, because it would make for a very messy, difficult to understand chart. But as you can see, for the first few, the units were selected, and there's a total of 10 of them. That means that we've decided to take a 20% sample. That's 10 units out of the 50 in the population. But that's how you can use randomization to select your sample. That's just one of the tools. And another of the tools, the trend charts, as you can see, you've got data points being collected on a, let's say that this is an X-bar chart, and what you've got is the target specification in the center. You've got your lower spec limit and your upper spec limit. They're identified on the right side of this graphic, and the points are plotted. And so we can see that one of the measurements that we, counts that we came up with, is out of spec. That means it's out of specification, below the lower spec limit. But we do have the trend line, the slope of all the points in there, and that's called, this whole thing is called a trend chart. Now we're ready to take a look at Pareto analysis. And there's a look at Pareto analysis. Little trivia. Pareto analysis is named after a gentleman who lived in the latter part of the 1800s, early 1900s, an Italian economist named Vilfredo Pareto. And Joe Duran, Dr. Joseph Duran, in one of his earliest books, had a chapter about the use of the Pareto approach to the 80-20 rule. 80% of your problems come from 20% of your problem sources. And he was encouraged to grow the concept, and he did. A lot of people think it should be called a Duran analysis, because he took the initial work that Pareto did and turned it into what we now call Pareto analysis. A great way to figure out, where our problems are. Now, in this case, if we were looking at types of defects, we see that defect G, whatever it might be, is the greatest has the greatest frequency of occurrence of defects in this particular process. And so we would normally think, well, let's do an analysis of defect G and see what's causing it. But suppose we did and we weren't able to find out what the problem was, we'd have to do what's called multi-level or nested Pareto analysis. So let's take a look at the up at the top left. We see that item W, which is like item G in the previous slide, item W occurred 36 times. But we analyze it, and we can't decide what's going on. So what we need to do is to do a flow down, and what you see in the center, in the circle, with the bar that's entitled 21, that means that as a subcategory, let's suppose you have, let's say, something that's happening, like particular kinds of defects, defect W, a subset of that, W1, is occurring with the greatest frequency, and that's 21. But we still can't figure out why W1 as a defect is occurring, and so we do a further shred out, and we do for defect W1, defects W11, 12, and 13. That's 1, 1, 1, 2, and 1, 3. And we find that that is occurs 12 times, which is twice the W1, 2, and perhaps we're fortunate enough that we don't have to do any more shredding or multi-level analysis, and we're able to determine what's the source of that problem. But notice, if you will, let's go back to the Pareto diagram in the center where the W1 has 21. If you take that 21 and the 10 just next to it, and the 5 just to the right of that, they sum to 36, which is the sum total of W up in the top left Pareto analysis. And so we've taken a look at the 36 defects and identified how they are occurring in terms of a shred out. And we see that 21 of the 36, about 2/3 of them, are in the category W1. And then we come down to the bottom right, and we have 12, 6, and 3, which sums to 21, which is the frequency of occurrence of W1. And we can see that W11 or W11 is occurring 12 times, which is 50% of the, approximately 50% of W1. So by looking at this and turning up the magnification, if you will, and looking at it in greater and greater detail, we're able to come closer and closer to identifying what the source of the problem is. Now, we're going to take a look at histograms, which is how we're going to analyze, one of the ways of analyzing the data for continuous or variable data. And there's a typical histogram with the mean, the median, and the mode. And all you good statisticians know that when the mean, median, and the mode are the same, that we've got a normal distribution. That doesn't mean everything's good. It just means it's normally distributed. And this is we've seen the class interval set up on the X scale, the horizontal scale, and the frequency of occurrence showing up on the vertical scale. And so I'm not sure what all I can say about the histogram that statisticians don't know, but it's a very important tool for analyzing continuous or variable data. Now let's talk about data stratification. The purpose is to convert a heterogeneous population into a collection of homogeneous subpopulations or samples, where heterogeneous is defined as composed of people or units with mixed attributes, characteristics, differing genders, ages, costs, inequalities, or education or experience. And that could be like you folks that are watching and listening to what I have to say today about making the connection. And then we have homogeneous, which is composed of people or units with the same or similar attributes or characteristics. You could also be considered homogeneous in that all of you have basically the same or similar education with regard to your knowledge of statistics. Data stratification becomes very important when you're analyzing large populations in order to better understand the population itself. Now let's look at cause and effect analysis. This is known as the fishbone diagram, and a lot of people say that the inputs are 5 M's in the E: machine, method, material, measurement, men and women, and environment. And each of those factors need to be considered as to why something is occurring, the problem or the objective. What we do is, as you can see on the bottom of the graphic, we identify the problem or objective. Then we position 3 boxes above and below the spine of the fishbone, 1 for each of the 5 M's and an E, and then attach all the boxes to the spine with arrows. And there's lots of software out there that you can do this with. I've done it a number of times with computer programs, and projected it up on the screen so that everybody who's working on this particular problem can see it being built up. Now let's talk about scatter analysis. Sometime back in the 1980s, Time Magazine had a great article about the high cost of maintaining their airline aircraft, and based it on age versus cost per hour of maintaining the various aircraft. And I've left those dots the same. In this particular application, just for purposes of demonstration, I was doing some work for an attorney, and you can see that the letters A through I, represent various attorneys. Some are junior attorneys, some are senior attorneys. And on the horizontal or x-axis, we have the average caseload in hours per week. And on the vertical axis, the average cost per hour to close a case. And you can see where the various points are, and you can create an upper and lower boundary and a center line to enclose the vast majority of the situations. Well, you see the letter E up there. That, by the way, that was an airline that doesn't even exist anymore, Eastern Airlines, and that was an outlier. It's because their aircraft were so old it was costing them a fortune to maintain their aircraft. But in this case, you can also see there was a cluster, so we have a lower, some points in the lower caseloads, and some, but at the higher caseloads, they seem to cluster. So I've used this so many times with different clients to help them to identify or better understand situations that they've encountered in which they want clarified. It also helps them to solve their problems. Now we're ready to talk about force field analysis. Traditional force field analysis is non-quantified. But one day I was with a client, and they said, well, if we've got 3 or 4 different or more, 2 or 3, 4 or more various corrective actions, how do we know which one is best? Well, I decided arbitrarily to use a scale from 1 to 5. And let's talk first about corrective action A on the far left side of the graphic. And on the left side of that rectangle are the positive forces. And on the right side of it are the negative forces. And we call it force field because we've got the arrows there either on the left or right side pointing towards that line in the middle. And, for example, let's suppose that we've got one aspect of corrective action A that is really terrific. It's excellent. And so we give that its top score, which is a +5. Another one we evaluate as a +3, and another one is a +2. And just below the shaded area, you can see that the sum total algebraically is a +10. On the right side of that same corrective action A, there was one aspect of corrective action A that is pretty bad. Not so bad they give it a 5, but pretty bad. So we gave it a -4. And another one that was very close to 0, but we gave it a -1, and that's a -5. So we've got a +10 and a -5 below corrective action A, with a net value of corrective action A being +5. And then we would go through and do the same thing with each of the other corrective actions. And let's suppose the corrective action B had a net of +9, and corrective action C had a net of -3. You say, is it possible to get negative values? Of course. There's some aspects of corrective action C that are positive, and they're placed there. And there's not only more, but perhaps some dramatically disappointing aspects or consequences of using corrective action C. It's like taking a drug where the side effects are so bad that you say, maybe I should just stay sick. At any rate, you can see going near the second row from the bottom of the chart that the net value of corrective action A is +5, and of B is 9, and of C is -3. And we want to select the highest score, and so we give that that red arrow pointing at +9, and that says corrective action B is what we're going to introduce as our intervention, and see if we can improve the situation and improve the process. Now, let's move away from the 7 QC tools and the relationships to each other, and we're going to look at connectivity between the voice of the customer, trees, the Kano model, quality function deployment, the 7 management and planning tools, and design of experiments. In each of these boxes, I've got a dashed line. And above the dashed line is what we're trying to do, and below the dashed line are tools that can be used to achieve whatever it is that we're trying to cause to happen. For the need to reveal new or replacement concepts, we can use the voice of the customer, the QFD House of Quality, the 7 management and planning tools, paired comparisons, and the Connell model. We're going to look at all those in just a second. Then that moves us over in to the center block in the top row, where we want to identify new or replacement concepts. For that, we would use TREES. TREES is a Russian acronym. The English acronym for the same thing is TIPS, T-I-P-S, the theory of innovative problem solving. And that's a whole aspect of continuous improvement that we have just begun learning in the last 10 or 15 years. The Russians started it right after World War II, and is growing in popularity. And if you want to read about it, I would recommend the TREES Journal, available online. Just go to whatever search engine you use and type in TREES Journal or just TREES, and you learn a whole lot about it. But it's the theory of innovative problem solving. Moving to the block on the far right at the top of the graphic, the next step is to prioritize and rank order new or replacement methodologies. For this, we can use paired comparisons and or the prioritization matrix. That takes us to the selection of the best or new replacement methodology. For that, I would recommend the QFD E-Series matrices. That takes us to the next step, which is the identification of the optimal level for controllable variables associated with the selected methodology. That you're going to say, that's something I as a statistician have heard about. And for that, we've used robust design and experiments. Next, we confirm the selection of the new or replacement methodology, and we use the QFD House of Quality to do that. And finally, resolve the detail level problems when desired parameters appear impossible to achieve. For that, we would go back to use TREES and then return back to the QFD House of Quality. And there's a note there at the bottom left. If you haven't already looked at it, it says, as with the 7 QC tools of continuous improvement, the output of one of the above tools or techniques becomes the input to the next. And that's the making the connection. Some of you have seen this before, others that may be new to you. Let's take it from top left to bottom right. It's meant strictly to be humorous, but it conveys a concept. Suppose a customer has proposed that this is what he wants or she wants. In the top row center, it looks a little bit different with the specification of the request for proposal. And just to the right of that, the way engineering designed it, and now down to the bottom of the chart on the left side, this is the way product operations produced it. And just to the right of that, the way the customer received it. But if the customer had used his or her head, what the user really wanted is pictured in the bottom right. And I'm sure that those of you working in healthcare or industry or education have all experienced something like that, even if you've never seen this chart before. And this is titled Responding to the VOC, the voice of the customer. The Kano model of customer satisfaction. Noriaki Kano, professor at the university in Tokyo. I first met him, I guess it was the early 80s at a Gold QPC conference in Boston. Very fine gentleman. And he came up with this, what's now referred to as the Kano model of customer satisfaction. It's two-dimensional. The horizontal axis goes from something, a product, a service, whatever you're looking at, doesn't do what it's supposed to, all the way over on the far right to it does it very well. On the vertical axis, we're talking about customer satisfaction. At the top of that vertical line, we have great satisfaction. At the bottom, great dissatisfaction. Now, on top of that, let's call it a plus line in terms of the horizontal and vertical axes. We have 3 levels of customer satisfaction. At the bottom right, we see the arrow that moves from the quadrant at the bottom left into the bottom right. This is called expected quality, frequently referred to as the musts or dissatisfiers. The next arrow, the one that goes through the bottom left to the top right, is referred to as normal quality, and therefore usually called the wants or the satisfiers. And finally, we have exciting quality, the delighters and exciters, the wows. You've heard the use of the word wow a lot, and people talking these days about certain attributes. And this is where it came from the Cano model. What we do is in QFD, the House of Quality, we talk about the musts, the wants, and the wows. That's expected quality, normal quality, and exciting quality. Now, you see those arrows up at the top right. Over a period of time, items that are exciting quality become normal quality, become expected quality. Think of, for example, the characteristics of an automobile. There's certain things that at one time were exciting quality. Wows, you could have a heads-up display, and then people come in and say, "Hey, my neighbor, my uncle has one of those. I want one." And finally, it gets to the point where everybody expects it. And so, over a period of time, there is a movement from exciting to normal to expected. That is, from wows to wants to musts in terms of attributes or qualities. Not quality, but the qualities of a particular product or service. And the last arrow at the top right is about the competition. When somebody comes up with something and everybody else needs to do it, or they're not able to compete. So there's always a move towards the exciting qualities, the delighters and exciters, the wow makers. And that's, for example, if one car maker or one washer or one home builder does something, the others see the result, and if it's a very popular thing that's been happening, they're going to move in that direction. And if it's not, then probably the person or the company that started it lets it drop, and they go on to the next exciting item. There's nothing that stays the same. And we're always trying to improve our competitive position. And over time, if you don't, you lose. Now let's talk about the voice of the customer tables. We have two tables there. Voice of the customer table A, which is also known as the customer segments table, and the voice of the customer table B, which is also known as the customer voice table. Let's use an example of a flashlight. Let's suppose that the customer verbatim, that is what the customer says for this flashlight, I can't see at night and there's a power failure. And the first thing you think of course, is a flashlight. Who is that person that said that? Well, that we put in the homeowner. What is the homeowner trying to do? He's trying to see. When? Well, it occurs at night. Where? Well, it might be in the basement or wherever you've got your fuse box or your electrical controls in your house. It could be a basement. It could be somewhere in a smaller back room. Why? Because you need to see in the dark to check the electrical circuits. How are you going to do it? Are you going to hold it in your hand or set it on a surface so that you can be looking at the electrical circuit box and see what's gone wrong, where a switch needs to be turned, for example. And that would take us to the voice of the customer table B. Some of the reworded demands, reworded from the verbatim. The reworded might be, I want to see, even if I'm using both my hands. And the demanded quality, it should be easy to grasp. It won't roll on a flat surface. It's easy to replace the batteries. How about the quality characteristics? It should be dependable. What's the function that you can see easily anytime you need it? Reliability. It should last at least a quarter of an hour. Other issues might include things like how many switch positions do you need in terms of the intensity of the light. But this voice of the customer tables, both A and B, are extremely important into better understanding the voice of the customer in terms of what they want, what they're looking for, what they expect in the product or service that you're trying to provide. The paired comparisons process. I do this with my clients using Post-it notes. Over on the left, let's say that there's we're trying to compare 5 different ways of doing things in terms of what's good and bad, what we like and what we don't like. We start out in phase 1 comparing any 2 items. And arbitrarily here we've selected item D and item B. And doing a comparison, which one is better, the process improvement team says, we believe D is better, and so we put the Post-its in order with D above B. Then, in phase 2, again, we arbitrarily select another one. In this case, we picked A, and we compare, I hold the slip A or the Post-it A next to D and says, which is better, A or D? And if the consensus is that D is better, then we bring it down and put it next to B and say, which is better, A or B? Well, in this case, A was better, so the resultant location is D, then A, then B. Moving on to phase 3, and you can see the pattern of how this is working. We take and hold the, we've arbitrarily selected C, and remember there's only 2 left at this point, C and E. And so we take C and hold it next to D, which is better, C or D? We say, well, D is better, so we hold it next to A, which is better, C or A? We say A, so we drop it down, put the C slip next to B, which is better, C or B? And the answer is B. So C, not arbitrarily, C is forced to be at the bottom. So now we have 4 of the 5 slips, D, A, B, and C in that order vertically. And finally, so it's no longer an arbitrary selection because E is the only one of the slips or Post-its left. And we start at the beginning and say, which is better, D or E? Well, in this case, we say E is better. And so we don't have to go any further than that because we already know that D, A, B, and C are already in order. And so we put the E up at the top. And we say we have E, D, A, B, and C. And now we have a paired comparison process completed. We call it paired comparisons because we always do 2 at a time. And I've used this so many times, it's very, very effective. Now, here's a prioritization matrix. The hardest part of prioritization matrix is making sure you don't mess up on the numbers. Let's say that there's 5 options down the left-hand side, A, B, C, D, and E. And what we want to do is just prioritize them and say which is the best one, which is the second best, third best, etc. Across the top, we have factors to consider. Cost, time, resistance to change, impact on the problem, and the row total, and finally the rank ordering that we're going to place in. We have a lot of discussion, and there are very easy ways to determine of the 4 items that we're concerned with, cost, time, resistance to change, and impact on the problem. We identify what proportion it should represent of our final decision. And after some discussion, we say that cost represents 26%, time 14%, resistance to change 1%, the impact on the problem 59%, for a total of, as you go across the top, 1. And then we go through, we're going to have to look at each of the cells in this matrix. For example, we've done the horizontal axis across the top, and in any one of the columns, we see that, for example, in option A for cost, the number 0.31, and in B, 0.12, and C the same, D 0.33, and E 0.12. Those all sum to 1. And what it represents is the importance of a cost with regard to A, B, C, D, and E. And again, those have to be discussed individually. Once that's been achieved, We now do some multiplying, and so we take the cost at 0.2. I'm looking now at option A, the cost column, and we know that the cost is, the factor is 0.26, and we multiply that times the 0.31 that we'd already identified, and the product is 0.081. And if we do that for option A in the second column, we take the 0.14, which is the factor for time, times 0.22, which has already been identified, determined, and multiply it, get a product. We do the same thing for resistance to change and impact on the problem. And if you take those four values, the four products of 0.081, 0.031, 0.001, and 0.171, the sum is 0.284. And that's in the second column from the right for option A. And we do the same thing for each of the other four options. And we end up with row totals for each of those, and then we rank order them. And we say that because 0.284 is the greatest, it gets a rank order of 1. Option C at 0.221 is rank order 2, etc. And the least one, of course, is option D, which had a very, very low total of all the products at 0.140, and that is a rank order of 5. And that prioritization matrix is really good. Use this many, many times, very effective, because what it does, it takes a lot of individually, let's see, I'm trying to see how I want to describe this. It takes individual aspects of a situation and puts them in context such that you don't have to make big decisions like which is the most important one, which is second most important. Just by looking at the original values, what we do is we break it down and say, okay, when you consider cost and time and resistance to change and impact on the problem and how those four factors relate to each other with regard to the options, what we do is we end up with that rank order, which is a much more scientific approach to providing an answer to our question. I see that we've only got a couple of minutes left, and I got about 5 or 6 slides left. So for those of you who can stay on, I'd appreciate it. And those of you who can't, you can always watch the video on YouTube that Amy will be placing on the net for everybody to see. So I'll continue talking and trying to finish this presentation. The benefits of QFD. This is the House of Quality. It's a requirements planning capability. It's a tool for graphic and integrated thinking. It's a means to capture and preserve the engineering thought process, a means to communicate the thought process to new members of the QFD team, and it's a means to inform management regarding inconsistencies between requirements, risks, and needs of the customer. God, I have used this so many times. Outstanding. It has a variety of applications. If you want to learn more about it, one of my books, the QFD Handbook, is available through Amazon, and it's on the subject of QFD. I'm told by Amazon that it's the bestseller on the subject of quality function deployment. Now look at the process flow for using QFD. Starting at the top left, we have customer requirements, design requirements, engineering design, product characteristics, manufacturing and purchasing operations, and finally production or quality controls. But what we do is take them two at a time, and what we then do is end up with a series of matrices that are a part of quality function deployment. The what's in the requirements matrix, which is the House of Quality, we have the customer requirements, which are the what's, and the how's, how are we going to meet the customer requirements, the design requirements, and then once we've identified the critical design requirements using the requirements matrix, they become the what's in the next matrix, which is the design matrix, and we analyze the design matrix with a focus on the engineering design. The design requirements are the what's, the engineering design results are the how's, which become the what's in the product characteristics matrix. And talking very quickly now, you can see as we move from left to right that we have a series of, in this case, 5 matrices, and all told, if you wanted to use all of them, they don't all have to be used every time. You might use 2 or 3 of them, or you might use 8 or 9 of them, or you might use all 30 of them. This is a graphic of a process flowchart I developed for one of my clients several years ago, and in an effort to figure out what new concepts need to be used. Starting over at the left, we have training and the quality function deployment. We developed at the top left, the development of the Gemba checklist. Gemba is the place, the Japanese phrase for where work is done. And you collect all this information in an effort to create the what's for the QFD House of Quality. And we create an E1 matrix, which is the what's versus new concepts. And we have to identify new concepts separately. And then in the center, we talk about creating a list of functions, and we use functions against new concepts. And then at the bottom right, bottom left, we create the machine house, and that along with the new concepts, we have an E3 matrix, which is the house versus new concepts, and we use the E1, the E2, and the E3 matrix all come together at the right to create the E4 matrix, which is the results, a compilation of the results of the E1, 2, and 3 matrices versus new concepts. And finally, we use all that at the finish point, bottom right, to create the A1 matrix House of Quality. Believe me, folks, it's not nearly as complicated as it may look. But what I tried to do is in one single piece of paper to put together everything you needed to do for new concept selection. You've all seen this. This is design of experiments, the run numbers down the left-hand side, the column numbers across the top, the various levels, the factor levels. And at the top, I've identified using colors for the 3 factors for this L8 orthogonal array. You've got factors A, B, and C in red, and in green, we have the interactions for a and a two-way interaction A and B, a two-way interaction A and C, and a two-way action B and C, and finally in column 7, a 3-way interaction with A factors A, B, and C. Orthogonal array. Orthogonal means at right angles. Here's an example: 3 factors at 2 levels. Full factorial with 2 factors and 3 factors at 2 levels results in 8 experimental runs. We'll look at that down at the bottom left in a second. A fractional factorial for the same situation would require only 4 experimental runs. Down at the left, just to the right of the circled numbers, 1 through 8, we see the 3 factors at each level. For example, we have 1 is A1, B1, and C1, so all 3 factors are at level 1. In the second row, factor A is at level 2, B is at level 2, but C is still at 1, etc. Those are portrayed graphically on the rectangle or square on the right, and you can see that circle 1, A1, B1, C1 is at the bottom right front of the square or rectangle. The 2 is over at the top left in the front, where we've got A2, B2, and C1. And so we have the full factorial representing the 8 corners of that rectangular square, whereas a fractional factorial, Taguchi's L4 orthogonal array, for example, is the first 4 rows. Now, if you don't want to use the first 4, use the last 4. But they all, both, either the 1 through 4 or 5 through 8, represent a fractional factorial of the full factorial. And over on the far right, looking at the graphic itself, you see the red dots, if you will, from point 1 to point 3, and from point 4 to point 2. And you notice if you compress them and put them together, it forms an X. Because you've got, with that X, what you've got is right angles, and that's where the term orthogonal array comes from. And let's see, we're getting close to the end. Here's connecting 2 problem-solving tools. Suppose you had a fishbone diagram, the cause and effect diagram with the 5 M's and the E, and 3 of the items are identified, A, B, and C, as being highly important in solving the problem that's at hand. And what you would do is take those factors, move them over to the in this case an L4 orthogonal array on the right side and the 4 runs, and you would conduct a design of experiments, go through, do the analysis to see what level each of those 3 factors should be at in order to minimize the problem that was being analyzed on the left. Finally, the connectivity chain. Here's a process flowchart on the top left. We've got 1 going into 2 and 3, going into 4, which is a decision block, with the negative going into block 3 and the positive going into block 5. On the left side, we have a tally sheet for attribute data, let's say in step 3. And there are 4 defects or mistakes, W, X, Y, and Z. Frequency occurrence for those attributes is listed on the right at 20, 25, 15, and 40, totaling 100. But suppose it was continuous data in step 3 and not attribute data. And we have the class intervals there on the right for the 5 classes A through E, with class intervals 0.5 to 0.59, 0.6 to 0.69, etc. And the number of occurrences that occurs in each of those class intervals for a total of 50. Then in the bottom row, what we've got is an extension of the tally sheet for the attribute data. And as we saw earlier in the presentation, when we're dealing with for attribute data, we've got defect W, defect Y, X, defect Y, defect Z, and you can see the histogram is formed, and you can see which is the most important in terms of the greatest number of defects. And if you need to, you can always use the nested approach to further analyze each of those various types of defects or mistakes. On the right side is a histogram formed from the tally sheet for continuous data, and you will see where something is peaking, and you can see whether or not you're in spec or out of spec, whether you're centered on the target specification, etc. So you can see that you can go either way, but you can see how the connection between attribute data and Pareto analysis, or between the continuous data tally sheet and the histogram. And I believe this brings us to the end. You can contact me at my directly at my email address, which is cactus, and there's an underscore between cactus and statman at yahoo.com, or you can go to my website, www.revellsolutions.com. Quality Press has produced one of my books, and I've been involved in about 20 books. Item H1216 called Quality Essentials. And for those of you who are just new to the world of American Society for Quality and its magazine Quality Progress, there is a couple of addresses that you can go to for both Quality Progress or the Knowledge Center within the American Society for Quality. And with that, I'm ready to turn it back to you, Amy.
Okay, thank you so much, Jack. That was a great presentation. I realize that we are a little bit over on our time. So we have a couple of questions here. Some people need to drop off. I respect that. The presentation will be posted on the division's YouTube channel within a couple days, and the address to find it is youtube.com/ASQStatsDivision. So youtube.com/ASQStatsDivision. So thank you everyone for joining us today. And Jack, if you have time to take just a couple of quick questions here, maybe we'll take about 5 minutes to sort of address those.
Absolutely.
Okay. All right. So on slide number 28.
Okay, let me move back.
Okay.
Is this the one?
Okay. Slide number 28. The question is, Are these spec limits or control limits?
Well, it could be either one, but in this case, I've identified strictly as specification limits because something can be out of spec, and a point as placed on a control chart may be inside the statistical control limits, but still out of spec.
Yeah, absolutely. Okay, thanks. And somebody else is asking, Jack, is there a part 2 to this presentation?
Not that I'm aware of. Well, I'd be interested in knowing why the question was asked.
There wasn't a reason given. It was just a question.
Okay, well, if somebody wants to go beyond just the presentation, they can find my article in Quality Progress in July 2010. I'm sure they can bring it up on the ASQ website.
Yes, or I was also going to suggest, Jack, I was going to say you could just reference your website there because you do have all of your webcasts there on your website.
Yeah, let me comment about that, please. It was just a day or two ago, and I may have mentioned this to you yesterday when you and I spoke. Somehow or other, WebEx, the people that ASQ have contracted with to record and distribute the 70-plus webcasts that I did for ASQ, had managed to change systems, and as a result, if you go to my website, www.revellesolutions.com, everything there is good except for one thing. If you click on the links for any one of those 70-plus webcasts that I did for ASQ, nothing comes up except you've got to register for it. And I talked to the folks at ASQ about that, and they gave me a big whoops, high quality there, a big whoops. They forgot to tell me about that. And so they're in the process of accumulating all that information and going to send it to me, and then I have to turn it over to my IT guy to get all those links put back on my website.
Okay, I understand. So for now, we'll just wait until that issue gets resolved. It looks like the reason that the question was asked, Jack, is because one of the earlier slides does say Part 1 on it.
It does?
I'm not sure which slide.
Nor do I. I have no idea.
But in any case, that's the detail that we can look at a little bit later.
Yeah,
let's see if there are any other questions here. Okay, somebody is asking this question. Are QFD and HOQ typically used in a design for Six Sigma type of approach?
Would you repeat that, please, and be more, speak a little more clearly with regard to the items?
Are QFD and HOQ typically used in a design for Six Sigma type of approach?
It can be. It's depending on what you're doing. QFD and the House of Quality, which is really talking about the same thing. House of Quality being the first of many matrices that's part of QFD. They can be used. I hate to use this phrase, but when I was a professor years ago at University of Texas, University of Nebraska, I always said, it depends, because there's so many contingencies that you have to consider. There's a place for using QFD and its House of Quality in many Six Sigma situations, but it doesn't necessarily have to be used in order to resolve a problem, a defect, a situation. So I can't say there's a universal application for it in all Six Sigma projects, but I can say there is a place for it where it should be used.
Okay, thank you.
Yeah.
Well,
I'm still looking for that Part 1 thing.
Okay, I think it was slide number 5, and basically I think the thought was, since there was a -1, some people may have taken that to mean Part 1.
Okay, now this is the first page of the agenda. Webcast Agenda 1 and Webcast Agenda 2, all part of the same telecast.
Okay, understood. Thank you. Well, excellent. It looks like we've answered all the questions. Thank you so much, Jack, for taking the time to present with us today and spend 15 extra minutes here discussing. So we appreciate your time. Our next webinar is expected to be in the last week of July, and those details will be announced on the division's LinkedIn group page, as well as our website and our email newsletter. So be sure to mark your calendar for those. And as I said already, this webinar will be up on our YouTube channel. And also, Jack has been generous enough to provide us with a set of his slides here.
I'm going to send you an excuse me, I'm going to send you an updated one that includes that new types of data -4 chart that brings types of data 1, 2, and 3 together on one page.
Oh, okay, great. So I'll send out the slides to all the attendees. And Jack, we have one. Somebody is wanting to ask one more question. If you have just a minute, I gotta run, but maybe we'll spend like 1 minute on this one. The question is, what do you think of TRIZ versus the TOC thinking processes for creative problem solving?
Well, the first one was TRIZ, T-R-I-Z. That's the theory of innovative problem solving, and it's a very high quality technique. But I didn't make out, what was the second one?
TOC.
Oh, theory of constraints. Wow, that's a good question. I've been asked a lot of questions before, but that's one of the best ones I've ever heard. Let's see. I think their applications are different. Innovative problem solving is to look for a new and better way of doing things. That's the trees or tips. Where the theory of constraints is an analysis of processes and where certain things have to be increased or decreased. I say they're both high quality techniques, but with different applications.
Okay. All right. Well, that's all the time that we have. So thanks again, Jack. I hope everyone enjoyed the presentation. Looks like we're getting a lot of positive feedback on the questions interface. So a lot of people are saying thank you and thanks for the great presentation. So we really appreciate you again, and I hope everyone has a great week.
Talk to you soon, Amy.
Okay, thanks, Jack. Bye-bye.
Bye, everybody.